For over 60 years, humanity has reached space the same way. Fire, explosions, violence. We strap ourselves to controlled bombs and hope physics doesn't change its mind. Rockets shake, fuel burns, metal screams, and every single launch costs hundreds of millions of dollars. But what if I told you there's another way? No fire, no explosions, no deafening roar, just an elevator. An elevator that climbs from Earth all the way into space. This isn't science fiction. This isn't fantasy. This is one of the most radical engineering ideas humanity has ever imagined. It's called the space elevator, and today, we're going to build it. Chapter 1. Why rockets are a dead end. Before we talk about elevators, we need to talk about the problem. Rockets are brutal. To send a tiny payload into orbit, rockets must lift. Fuel to lift fuel. Fuel to lift that fuel. Fuel to lift that fuel. Over 90% of a rocket's weight is fuel. It's inefficient, dangerous, expensive. Every launch destroys a vehicle worth hundreds of millions. Every mistake is catastrophic. And if humanity wants to live in space, build space stations, colonize the moon, reach Mars, rockets alone will never be enough. We need a highway to space, not a cannon. Chapter 2. The wild idea that changed everything. The idea of a space elevator is older than rockets themselves. In 1895, Russian scientist Konstantin Tsiolkovsky looked at the Eiffel Tower and asked, what if a tower could reach all the way into space? At the time, it sounded insane. Steel couldn't do it. Concrete couldn't do it. Physics laughed. The idea was shelved for decades, until the late 20th century, when scientists realized something shocking. You don't need a tower. You need a cable. Chapter 3. The basic idea, simple but mind-bending. Imagine this. A cable thinner than a road, stretching from Earth's surface, straight up into the sky, higher than planes, higher than satellites, higher than the moon's orbit. At the top of the cable, a massive counterweight floating in space. The Earth spins. The cable stays stretched. Now attach an elevator car to that cable. It climbs. Slowly. Silently. No fuel. No explosions. Just electricity. This elevator carries people, cargo, satellites, directly into orbit. Space becomes accessible, like taking a train. Chapter 4. Why the cable doesn't fall. This is where most people say, wait, that should collapse. It doesn't. Because of centrifugal force. The Earth spins once every 24 hours. Anything far enough out wants to fly away. The top of the cable is pulled outward by Earth's rotation. The bottom is pulled downward by gravity. These two forces stretch the cable tight, like a guitar string under tension. As long as the center of mass is above geostationary orbit, about 35,786 kilometers above Earth, the cable stays upright. No supports, no magic, just physics. Chapter 5. Where would we build it? Not anywhere. The space elevator must be built at the equator. Why? Because Earth spins fastest there. Maximum centrifugal force. Maximum stability. The best proposed location? The Pacific Ocean. On a floating platform. Away from earthquakes. Away from storms. Away from populated cities. If something goes wrong, it falls into the ocean. Controlled. Contained. Chapter 6. The biggest problem, materials. Here's the brutal truth. Everything we've talked about so far is easy. The hard part? The cable. To survive, the cable must be stronger than steel, lighter than aluminum, flexible, resistant to radiation, resistant to micrometeorites. Steel snaps. Kevlar stretches. Carbon fiber isn't strong enough. For decades, this single problem killed the idea, until scientists discovered something extraordinary. Chapter 7. Carbon nanotubes, the miracle material. Carbon nanotubes are tiny cylinders made of carbon atoms. They are 100 times stronger than steel, extremely lightweight, flexible, electrically conductive. On paper, carbon nanotubes are perfect. The problem? We can't manufacture them in long, flawless strands. Yet, a space elevator cable would need to be over 100,000 kilometers long, with near-perfect atomic structure. One microscopic defect, and the entire cable could snap. This is why the space elevator still doesn't exist. Not because it's impossible, but because we're not good enough. Yet. Chapter 8. How would we actually build it? We wouldn't start from Earth. We'd start from space. Step 1. Launch a relatively small spacecraft into geostationary orbit. Step 2. Deploy a thin seed cable downward toward Earth and upward into space. Step 3. Anchor the bottom to a floating platform. Step 4. Send robotic climbers up and down the cable, thickening it layer by layer. Slowly, carefully, over months or years, the cable grows stronger, until it's ready. Chapter 9. The elevator cars. Yes, they climb. The elevator cars are called climbers. They don't use fuel. They use electricity, likely delivered by laser beams from the ground, or solar power. They climb at about 200 kilometers per hour. That means reaching orbit would take 5 to 7 days. No G-forces, no violent shaking, no danger of explosion. You could walk around, sleep, look out the window, watch Earth shrink beneath you. Chapter 10. What the journey would feel like. Day 1. You rise above clouds. Storms look like swirling paintings. Day 2. The sky darkens. Stars appear even during daytime. Day 3. You feel lighter. Your body adapts. Day 4. Earth becomes a curved marble. Day 5. You cross geostationary orbit. From here, you are no longer bound to Earth. You are in space, without ever firing a rocket. Chapter 11. Why this changes everything. A space elevator would rewrite civilization. Cost reduction. Rocket launches. $10,000 plus per kilogram. Space elevator. Possibly $100 per kilogram. That's a 100 times to 1,000 times reduction. Mass space construction. Massive space stations. Solar power satellites. Moon bases. Mars missions. All become practical. Environmental impact. No rocket exhaust. No ozone damage. No fuel waste. Clean access to space. Chapter 12. The dangers no one talks about. This is not a utopia. The space elevator is fragile. Micrometeorites, tiny particles moving at tens of km per second, could slice the cable. Solutions include redundant strands, self-healing materials, active monitoring, weather, lightning, winds, hurricanes. The base must move to avoid storms. Space debris, old satellites, junk, bolts, all moving insanely fast. A single collision could be catastrophic. Chapter 13. What if it breaks? The nightmare scenario. If the cable snaps near Earth, it falls, but not straight down. Because Earth is spinning, the cable would wrap around the planet like a whip. This is why location matters. Over the ocean, away from land. Engineers designed the system so that the cable breaks in controlled sections. Most of it flies outward into space. Minimal damage occurs on Earth. Still, it's a risk humanity must accept. Chapter 14. Who is actually trying to build this? This isn't just YouTube imagination. Organizations and countries researching space elevators include NASA, Japan's Obayashi Corporation, International Space Elevator Consortium. Japan has publicly stated a goal of building one by the late 21st century. The science is real. The question is timing. Chapter 15. What a space elevator means for humans. This is bigger than engineering. This is psychological. Space stops being far away. A child could look up and say, "I want to go there," and actually mean it. Space becomes reachable, routine, human. This is the moment humanity stops being planet-locked. Chapter 16. The next step, space economy. With cheap access to orbit, space manufacturing becomes viable. Zero-gravity medicine explodes. Asteroid mining becomes realistic. Solar power satellites beam energy to Earth. Space stops being exploration. It becomes infrastructure. Chapter 17. Why we haven't built it yet. The answer is simple. We are one material breakthrough away. The physics works. The math works. The engineering concepts work. The materials aren't ready yet. But history shows something important. When humanity finds a reason powerful enough, we solve the impossible. Chapter 18. The day the elevator opens. Imagine the day it happens. No countdown. No explosion. Just a quiet machine climbing into the sky. News headlines read, "Humanity builds its first bridge to space." That day, Earth becomes smaller, and the future becomes much bigger. Final message. For thousands of years, the sky was a ceiling. Then rockets punched holes in it. A space elevator does something different. It builds a door. A calm, permanent door. Between Earth and the universe beyond. No fire. No violence. Just engineering, patience, and imagination. The question isn't if we can build it. The question is, when will we decide to stop exploding ourselves into space and finally take the elevator?